All right. Hello, everybody. Seems like somebody turned on the noisemaker and everybody kind of got quiet and sleepy, huh? So today might be slightly shorter. Get you guys out and onto the rest of the week to the fall break a little sooner, I think, because we covered this already, this problem from last time. And I basically just want to finish up the membrane filtration section unit. So we'll talk a little bit about some of the math that goes into how to look at pressure as a function of essentially how much space the water has to go through your membrane and how fouling affects that. We're taking sort of a high-level approach, so it's not truly getting down to the nitty-gritty physics of fluid flow through these pores, but we're going to take some equations that have been developed according to that kind of physics. So that's sort of the context today. We talked about this dead-end filtration example last time where we pushed a certain amount of water through a filter, and it was essentially a mass balance at the end of the day. It was just flavored by the fact that we were using a membrane to separate the concentrations. Okay, so when we want to talk about the solute balance, when we do split water into two different streams, which would be that concentrate, so we're concentrating some of it, and then we're getting that cleaner permeate. If we want to talk about on a solute balance, how do we refer to that? We can describe the fraction rejected, and here I'm going to use uppercase R as the fraction rejected, and have that equal to 1 minus the concentration in the permeate divided by the concentration in the feed. So just briefly, we have some sort of membrane system. Some of it is rejected. That's going to be our concentrate. Some of it makes it through. That's our permeate. And of course, we've got the feed. So to think about what fraction is rejected, without looking at the formula here for a moment, the fraction rejected is going to be essentially whatever mass is in the concentrate, right? So I'll say concentration in the concentrate, right? C in the concentrate or the retentate. So that'll be the portion that's in the retentate divided by the portion that was, or the total amount, right? C in the feed would be one way to look at it. So we can rearrange that by doing a mass balance to get that 1 minus Cp over Cf. So I'm just trying to illustrate that there's a few ways to think about it. If you look at the Cp divided by Cf, that's the portion that made it through. So 1 minus the portion that made it through is going to be the portion that did not make it through, right? So this is portion rejected. And we can say this guy is the portion that went through, that permeated. Okay, so I'm giving you this equation on your sheet. I just want you to know essentially kind of what it's talking about and where this is coming from on a practical standpoint. Again, the C here is concentration in one or the other streams there. There's another way to describe it if we need to deal with very high percentages, so something like 99.99% of the particles rejected, which is pretty often the case. Let's say if we're removing viruses, some sort of an ultrafiltration membrane, maybe we're interested to make sure that we have the ability to take a viral load from millions of viruses for every liter and drop that down to at most, let's say 1,000 viruses per liter. Some could make it through if our pore size, maybe there's a few pores in our membrane that are a little larger than we expected, or maybe there's a tiny tear somewhere. So our membrane is not perfect. And so maybe we have some variation and we don't get perfect rejection, So we might describe this as, oh, we've tested it and we can remove 99.99%. To make that language a little simpler, we can use the log terminology and say, oh, let's just say R log, so the fraction rejected in log terms, and say that's just going to be the logarithm of essentially what's in the feed divided by what's in the permeate. So that's the ratio there, the feed over permeate. That's like how many times more do we have in the feed than we do that made it through. And by taking the log of that, that gives us a, let's say, I'll describe this a little better. So this is going to be the amount in feed divided by the amount that escaped. So this is kind of like, it's the inverse of the ratio that made it through, right? So this is like, I don't know if there's a convenient way to say that, but we can imagine if we have 10 to the 6, let's say, viruses per liter, as an example, divided by, so that's how many were in the feed, and we divide that by 1,000 viruses that made it through per liter, just as an example, then that is going to give us, well, the answer would be, or the ratio here is 10 to the third, right? Then you take the log of 10 to the third, it's going to be 3, right? 3 to the what, or so 10 to the what equals this guy, right? And that would be 10 to the third. So that's a way to simplify how we describe a fraction that's rejected. Because this means that if we had only 1,000 make it through and we started with 1,000,000, that's a 99.9% removal. So as I've written down here, in this example, well, let's say, for the sake of consistency with that example, I'm going to change this a tiny bit. Let's say only 100 make it through, okay? Sorry, did that backwards. Should be 4. So if only 100 make it through, we are left with 10 to the 4th remaining. Log of 10 to the 4th is 4, and that fits right in with this example here. And this is algae instead of viruses, but you get the picture. So in that case, we could write the R as 1, R from up here, 1 minus C in the permeate, which was 100 per liter, divided by, in that case, it was 1,000,000. So you see here, we could just add a couple zeros to make it consistent with my example. Same thing, right? Either way you go, that's 1 minus that ratio, and that ratio then, so the ratio by itself, without the 1 minus, would have been 0.0001. You add in the 1 minus that, that's 0.9999. And rather than tracking how many times did I just say 9 in your head, you just say, that's 4. 4 times. I said it 4 times, or I was supposed to set it 4 times, right? Easier way to handle it. So it's pretty straightforward. Just want you to know kind of what's happening with that in case you need to use it. Yeah.
When you say remove, is that like the amount that permeated or the amount that didn't?
Okay, so when I say removed, I mean that's the membrane removed them from the stream that's permeating, because that's what we're usually interested in. Not always, I suppose, but yeah, it's like the membrane is removing it from the clean water. Okay, make sense? All right, so that's pretty straightforward. Just another way to formalize the way we're talking about how the membranes are working and kind of describe the the systems in terms of the solutes or whatever stuff is in there that we're dealing with. The other way to look at it would be a water balance. So we have another R, just keeping consistent with the book. This is not actually our main textbook. This is one of the ones in the syllabus. So if you want more information, I'm happy to get that for you or post it. Essentially what I'm covering in class should be enough to get you through with no problem. So the lowercase r for water recovery rate, this is simply going to be how much water are we recovering on a basis of we feed our membrane a whole bunch of water, and then some of it gets rejected and goes to waste, and then some of it is produced as clean water. So we're looking at that ratio of produced clean water compared to how much we fed it in total, right? So that's clean over total used. Okay, so pretty straightforward. If we don't have to backwash very often or very much, then it should be a pretty high number, right? So sometimes maybe we'll get like a 90% or more water recovery rate. Other systems, maybe you need more cleaning. Maybe you're not getting a whole lot of permeation. You have to send a lot through your concentrate line. So that's another thing, right? So your concentrate line, it's not just the backwash and stuff, but it's really more so how much water is going through the concentrate, carrying away the dirty stuff. If half of your water goes that way, you're not very efficient in terms of water used. Okay, so then just a side note here, when we are talking about some sort of a membrane system, and we have the three directions to go, we have a QR here, QP, and a QF. Essentially, QF is going to be equal to the sum of the other two, right? We have a water balance. That's all I'm reminding you here, is that we have conservation of water across the system. And so when we are doing any problems involving recovery rate, or maybe you don't know the flow in one or the other, you can be confident that you can find that flow, just simple water balance here. Okay, so if you're treating 100 milliliters per minute of water and 15% of it goes to waste, the R then is going to be 0.85, right? So here we say out of those 100 liters per minute, 85 of them make it through as clean water, and 15 of them go elsewhere. So you could write that as QF equals 100, Q for the waste, that retentate we were given as 15, and then in this case you could say QP is 100 minus 15, which equals 85, and then you take 85 over 100, 0.85, right? So it's very simple. I'm just elaborating, hopefully to make that abundantly clear there. And these, of course, would be liters per minute. And then this would be just a ratio. So that's, this. Okay. All right, so that all is just kind of straightforward ways to talk about our solutes. So now we get a little more interesting. We talk about flux. So we talked about flux within the granular filtration topics, really that a flux is some amount of stuff going through a given area, right? And given that it's a flow through an area, then we can simplify that to essentially be a speed or a velocity, right? So if we have, in this case, liters per square meter per hour, that's some amount of stuff that's traveling through some plane, right? And you've got some area, you've got some quantity over time, so some volume over time. Through that area, that's your flux, right? So you could write it as cubic meters per square meter per second, for example, or simplify that to meters per second. Or maybe you want to use liters, and that's just more convenient, so you leave it as liters per square meter or per square foot or whatever. The units, although you need to care about them to keep them consistent, as long as you have a flow through that area, you've got a flux. So here we use J to denote flux. And if we take J as that for a membrane, what we're doing is we're taking it and putting this water through the surface area of the membrane itself, right? So even if it's what we talked about last time, like a spiral bound membrane or some non-flat sheet membrane, we're still pushing it through some surface area. So we're still having a flux through the area, even if that area is interesting, has an interesting design, right? So whatever happens with the area, it's still an area, we still have a flux. And so what we're interested in is actually not the flow rate leading to the membrane, but the flow rate going through it, right? So because this is a flux through an area, that means we actually have to use QP when we're talking about, so if this is volume over time, that's a term for Q, right? But this is Q that is permeating. Because the flux is the amount that's going through the actual membrane, right? So there's going to be some that doesn't make it through. So when we talk about flux, keep in mind that it has to be that amount that's going through it rather than the total that meets it. Okay. And one more reminder, we know the flow rates are, we're not going to have any weird disappearing or appearances of flow rate along the way. Okay, so this brings us to an example problem I'd like you to try solving. It's a bit of geometry, but essentially we've got a system here. We have to know something about the surface area for the membrane. So I'll get you started a little bit and then let you get going on it. Essentially, I'll read it and then I'll give you a starting point. So we have this Dow FilmTech SFX 2860 membrane module containing 5,760 fibers. So we've got this hollow fiber membrane. One unit has almost 6,000 of these little fibers in it. They're each 1.87 meters long with an outside diameter of 1.3 millimeters and an inside diameter of 0.7 millimeters. So the problem then says calculate the water production from one module, so one module containing all these fibers, if the flux is 75 liters per square meter per hour. And the flow direction is either 1, or A, you could say, outside in, or B, inside out. And then it asks you to compare the two answers. Okay, so I'm going to recommend when you meet a problem like this, again, always draw it out. We've got some hollow fiber membrane. This is just one of the fibers, and we know the length is 1.87 meters. We have a couple of diameters, and in fact, I'm going to make another drawing here and say pretend those are nice circles. We'll say that inner diameter, that was 0.7 millimeters, whereas the outer diameter was 1.3 millimeters. Okay, so we have a flux. We know that so far what we learned about flux is this is going to be the flow rate that's permeating through the area of our membrane. Okay, so we were given some information about the number of fibers, given some dimensions for our fibers so that we can know something about their filtration, the area that we can use as a filter. So, and by the way, we're either going to be using the outside as a separation layer or maybe the inside based on which one the water is meeting first, right? So if we operate inside out, that's one case. If we operate outside in, the water is flowing in a different direction and we have a different surface that's giving us the separation. That's really the tricky part of the problem. Okay, so now what we need to find is the water production. We were given a flux. So the flux was 75 liters per square meter. Water production, if you think about that term, that's what we're asked for. And It's worth taking a moment to consider what would you think that meant. I'll tell you in just a moment, but think about that for a second. And perhaps it helps that I already wrote some of it out. So QP should be our water production, right? That's the amount of water, the flow rate of water permeating through the membrane. So that water production, it's not a very technical or precise term, but it's a rate at which it's produced, right? Which should be the QP. Okay, so I'm going to give you 5 or 10 minutes to work on this. So as you see, I've worked it out here. Essentially, we need to take these hollow fibers, find the surface area of one of them, multiply that across the 5,760 of them in our module, and take that total module surface area and apply that to essentially to our flux, which was 75 liters per square meter, to get our water production, right? So that's our flux times the area. And as long as we have everything in meters, well, we can get an answer in liters, that's fine. But the surface areas need to be in liters, meters. So if we take the length, meters times 2 pi r, so that's our circumference of a circle. So pi times diameter. So it'll be 1.87 meters times pi times in the outside in. That outside is going to be doing our filtration. So that's 1.3 times 10 to the minus third meters. So millimeters, a thousandth of a meter, times that number of membranes, little hollow fibers, gives us a total surface area for the module at about 44 square meters. Whereas if we take it with the inner side, we can even see based on the size difference, right? It's a 1.3 millimeters versus 0.7 millimeters. It's almost 2 times as big of a surface area just by using the outer diameter here, because these are such small fibers. If you think about it, and you were to consider that the difference in surface area, if you had a much bigger tube, let's say 1 meter, and the thing is like a millimeter thick, the difference between those are going to be almost nothing, right? So it's partly because these fibers are so small that the thickness of the tubes themselves makes it such a big difference. So it's about a factor of 2 almost difference. And since that surface area is directly proportional to the water, we can expect our second answer to be about half, a little over half of the first answer. So looking at the areas, it's about 44 compared to about 24. And that corresponds with fluxes being about 3,300 liters per hour versus almost 1,800 liters per hour. So kind of exactly what we expect. Any questions? Yeah. 2 pi r is the circumference of a circle. So to get the surface area of one of these cylinders, we need the length times the circumference. So it's essentially a cylinder, right? So we have that length, and to get the surface area, we need to know essentially the distance around and multiply that by the length of it. So,
but the R that is the radius, not the diameter.
Yes. So what I did in the equation then is I said, well, so 2 pi r here, the 2 times r is the diameter. So rather than include the 2r, I just use diameter here, accounting for the 2r. I could have divided the diameter in half and then put in 2 pi times diameter in half, but I just did it that way. Yeah. Good question to clarify there.
Probably that is, the question shows that diameter that is 1.3 millimeters. So that is, if the r that is should be divided.
So for the radius, so for my drawing up here, right? If I took the radius of the inner circle, actually, I'm going to do this in a different color just to be clear. So if I take the radius of the inner circle, the r should be 0.35, right?
Yes.
And the radius for the bigger one, let's do this. Would be 6.5. Okay, so that's what you're saying, right? Yeah. So then, in the equation here, all I have to do is say instead of 2 pi r, all I'm saying is 2 pi r equals pi times diameter. Right, so I just left them alone and just dropped the 2.
Because they're too confusing.
Yeah, sorry. So I was trying to remind everybody that 2 pi r here is the circumference of a circle. That's why I went ahead and left it in that terms, but since I already had diameter, I just used that. All right. Okay, so let's talk about the driving force behind operating a membrane. That would be our pressure. I think we talked about it briefly last time that you can use gravity. You could potentially draw a vacuum. You have some limitations there for the vacuum. You can only have as much pressure as you have atmospheric pressure if you're going to do that. But you could just take a pump and just hammer on the water until you get a really high pressure. Water is practically incompressible, so that works pretty well for pushing it through a membrane. And what we call that force in the context, or that pressure in the context of a membrane, would be transmembrane pressure. And so you can actually discern a pressure drop from before and after a membrane because it has kind of consumed some of that energy to force it through in a way. So we will talk about pressure drops, or this transmembrane pressure, kind of a delta P. For our sake, I'll typically refer to as TMP, transmembrane pressure, and I'll be defaulting to pascals for those units so that we can use a few of these equations. Of course, some of the equations you could use a dynamic viscosity term in a different unit and then use a different unit for your pressure, for example, but I'm just going to keep everything this way to use pascals and to use the same dynamic viscosity units that we have been using and values. So in this case, we'll say our delta P, this transmembrane pressure, is the pressure that exists before the membrane in the feed minus the pressure that remains in the permeate. Okay, so pretty straightforward here. It's worth noting that you can have systems that you have feed into some membrane that goes into a second membrane and so on. And you can drive all of that with a pressure at the very front, and each of these membranes will cause their own little pressure drop. And so you could have sequential pressure drops, and any one membrane is only providing some amount of resistance. And then you have the series. Of course, you could add a pump to pressurize further in the middle or whatever. That kind of operation is pretty common, especially because we will usually want to avoid sending large particles towards very, very fine pore size membranes. We don't want to damage the pores on the really delicate, fine pore sizes. So typically what we'll do is we'll operate with something like a microfiltration, then ultra, then nano, some sort of a sequence, because it doesn't cost a whole lot to do those larger ones relative to the very, very fine pore sizes anyway. So you might as well protect the membranes that are the most expensive and require the most pressure. So that's typical, is to operate in that manner. So you'll have like a microfiltration membrane with a very small pressure drop, maybe then an ultrafiltration, moderate, small pressure drop, then getting into your membranes that really require a whole lot of pressure. And so the membranes then, really what they're handling is the pressure difference between the feed and the permeate, because there's still going to be a lot of pressure in the pipe, in the permeate, and the membrane just needs to be able to withstand that difference. Okay, so when we have to operate a membrane at a very large pressure difference for a very small pore size membrane, that's where we have the big risk of squashing that membrane, right? Because otherwise, we try to pressure up and up and up, we'll just have faster flow essentially through a larger pore size membrane. So they don't typically have that same problem. Okay, so how does it relate technically to the flux, this pressure? You think, okay, well, we ramp up the pressure, we get more flux. Well, that is true in a sense, and here's our relationship. We have the flux equal to this transmembrane pressure divided by the membrane resistance times the dynamic viscosity of water. And don't listen to these units here, because that was just an example of what kind of units we have with flux. If we check this, the units should be different, and I apologize for having that there. So if we are saying we have pascals over this RT, which is going to be, this is the membrane resistance. We'll talk about this in a moment. This total membrane resistance is in per meters. So we have meters to the -1 here. And then we have dynamic viscosity of water, which is kilograms per meter per second. Then, I need to remind myself even, what are the term pascals at Newton per square meter? Is that right? What are the technical units? I should know this, right? We all agree I should know this. So I'm going to look this up to remind us all. You got it?
Wouldn't it be kilogram meter per second squared divided by meter squared? So then it would be kilogram per second squared per meter?
Yes. And so double checking online, yeah, kilogram per meter per second squared. Right? So Pascal should be kilogram per meter per second squared. Yeah. Yeah. Okay, so then let's take this and divide it by those other ones. Per meter times kilograms per meter and second. And so this should give us units here. Let's see. Kilograms should cancel. This meter would go down and join this one essentially. And then those would come up to the top. So we'll have, say, meters on top per second squared. This second will come on top. So that'll be, cancel that. And we're left with meters per second, if I've done that correctly, which, the same thing, we could also say cubic meters per square meter per second. So yeah, these, don't listen to these. That was just an example of what a flux unit is. Okay, good. So that works out. I should probably revise my notes a little bit. So when we solve a problem then with pascals, this R is in meters, and our dynamic viscosity, then we should be left with cubic meters per square meter per second as our flux. Okay, so that's an elaboration on the units here. But essentially, the flux then is that pressure difference divided by how hard it is to push water through the membrane, which is a function of how much resistance is there and how viscous the water is. So if you were trying to push honey through a small space, you can understand that's not going to work very well. But if you maybe heat it up a lot, so it's more, it's less viscous, it's easier to flow, it would be easier. Same thing with water. If it's highly viscous, it'll be more trouble. So talking about that membrane resistance then, here's kind of a physical picture of what that means. These are electron micrographs, just basically fancy microscopes that let us see kind of what's happening at a very small level. You can see this little scale bar here is 50 micrometers, for example. So essentially, most of our membranes are going to be structured in a manner similar to this, where we have these larger pores that you see here. Water should be able to relatively freely flow through those. And if this scale bar is 50 micrometers, and that's tens of micrometers there in diameter for those pore sizes. So this is really what I would call the structural support. And it's designed to hold So we could call it a support layer. It's designed essentially to hold up the separation layer while offering minimal resistance to the water that needs to flow through it. So then up here above, you see these very much smaller pores. The entire material gets like really very compact and dense. There are pores there, but as we see using the scale bar, they're easily, as small as a micrometer, maybe a couple micrometers, but they're very small, and that's going to be our separation layer that's providing most of the resistance for flow through this membrane. And you can see this throughout most of these pictures. They have some form of that, right? This is maybe the clearest one you can see, but this guy also seems to have a separation layer right there. This one here, we can clearly see these are getting more and more fine as we get closer to the surface, and perhaps that really small layer there is even smaller. This one's got a kind of a network of holes everywhere in here, and then a really, really tight, compact layer right here, across the board, and so on. And so that's kind of the typical way of designing a membrane. And so then one thing you'll notice is, while you could do filtration in either direction, it's going to be a lot better if you do filtration in the correct direction, because you don't want all your dirt particles and whatever you're trying to remove getting stuck inside the support layer. Because if you're flowing water through this way, all of those particles are getting stuck inside here, and then you've got a membrane resistance. First of all, you're not going to be able to backwash them off of there very easily because they're stuck inside. Second of all, you've got this deep layer of stuff you have to push water through now. Whereas if you were operating it in the correct direction, then I'll use this other one as an example, then all your particles that are going to get stuck are on the surface here, and everything else just slides away, right? So that's the better way to operate a membrane. That's by design. And so when we were thinking about our inside out versus outside in operation earlier, we'd better hope that either they have a separation layer like this on both ends, which would be kind of weird, or that you have specifically designed these membranes for one or the other operation. Because that's actually the more typical way of doing it. Okay, so one more visualization here, and we'll add in what happens when you have fouling. So all the dirt and the grime, other particles, maybe bacteria start growing. We call this all fouling, membrane fouling. So sort of like when we're operating a granular filter and they get clogged up with particles, membrane filters have fouling. And it might just be molecules that are accumulating and starting to crowd out the pores of a membrane. Perhaps it's a little bit microbial, perhaps it is physical particles. Okay, so let's pretend we have a membrane here, and I'm going to draw it a little bit to try to get a picture that looks a little bit like what we were looking at just a moment ago, where we have larger pores on one side, and then these smaller pores here for the separation layer on the right side of this schematic. Okay, so that gives us a system where we have flow kind of going from right to left in this case. So flow will be going in this direction, at least when we're going through it, right? Because this then is the separation layer. So as we have water flowing through, I'm going to classify 3 different types of resistance to the flow that we can think about. Of course, there's also going to be flow that sort of, I guess we could say Q, R goes this way, whereas QF would be here, and then QP would be coming through here, right? So that's kind of the schematic for my membrane right here. Okay, so let's break this apart into 3 segments and say that if we have kind of 3 areas to consider, we'll say, first of all, just the membrane resistance, R of M, that's resistance in a clean membrane. Nothing has happened yet. That's just the natural properties of the membrane. It just has some resistance because it's hard to push water through it. So that's the component. So if we take the total resistance being the resistance of the membrane plus the resistance due to fouling plus resistance due to what we call a cake layer, that's going to be our total resistance, and that's in per meters. It makes a little sense that it's in a per distance because it's some portion of, energy, of resistance, of something per distance that the water has to pass through. So that's a way to make some sense of why it's in a per distance manner. So then we have some fouling. So when we get fouling, it's going to start clogging up some of these pores, and it's going to be material starting to clog in and around the edges of these pores. And so you can see just the way I'm drawing it now, it's kind of making it a tighter packed scenario. And it's harder to push water through it because the pores have literally been constricted. Okay, so the filtration outcome in terms of what kind of particles we can reject might have actually improved. The pore sizes have shrunk in general. So we might actually have better filtration in the sense of how clean the water is. But in terms of how much pressure it's required to do that, it has gotten worse. So that would be kind of our typical definition there. That would be the RF. And last, then, we would have what we call cake layer formation. And that's essentially when we have particles starting to, we're going to have some RF regardless, but the cake layer filtration really refers to once particles are starting to stack up on the top of it. And essentially, we're making a new network of very small pores for water to pass through. So now we have what's called cake filtration, where this layer of dirt and grime on top of the membrane is actually acting like a membrane itself. And we've got then filtration through that cake layer, and that's an entire different type of resistance to look at. Like I said earlier, there are people that go really, really in depth on the researching each of these areas and how they affect the physics and how to describe all that with mathematics and stuff. For now, I'm just going to say each of these can contribute, and that they're all piling into the same membrane resistance, which goes back to essentially that concept where we said the flux is equal to the transmembrane pressure, the pressure that we push divided by this resistance that we're talking about. So this is all resistance to the flux, so we have to add more pressure to get the same flux. So this kind of describes as well why membrane cleaning is important. For membrane operation, it's a little different than granular filtration. Granular filtration, we often had systems where we would take it down for 20 minutes at a time or more to physically push all these particles out and away. For membranes, it's sometimes we backwash, but it's a little more, it's a lot more frequent typically, where we'll be operating, and we'll take 20 seconds to push clean water backwards through it and try to push off some of this cake layer. The fact that we have this retentate stream should gather most of the rejected stuff in the first place. So what we're building up is not like days and days of just all this grime had nowhere else to go. This is actually just trying to knock whatever we can off of the membrane. So in fact, sometimes it'll be every minute or every 10 minutes, 20 seconds of backwash. So it's just a quick clean it off, shake it off, try to do something to physically dislodge it. And then let's say for some filters, then every few months or maybe once or twice a year, you'll take it then and chemically clean it with some acid-base steps, maybe with some sort of detergent or bleach, temperature, whatever your membrane is capable of handling, and whatever does a good job removing resistance that tends to gather on that type of material, you'll do that. And that will restore a lot of this interstitial fouling, the RF here. Whereas backwashing typically does a decent job taking care of that, the cake layer. Okay, so just a little bit better diagrams that I'm not, that I sort of drew here for you a moment ago. There's a couple different ways to describe what kind of fouling you have. We could completely block the pores, the complete blocking, the standard blocking. All of these are just different components of either that membrane resistance, the RF, or the, as we see, the cake filtration here, where water literally has to go through the pores to get through. So there's intermediate blocking and all that. There's one other term here that we might use, and that's called permeability. Well, that'll be uppercase L subscript P. So basically the permeability of the membrane, and this is just kind of the inverse of what we were just talking about. It's how permeable is the membrane? Well, that's the flux divided by the amount of pressure it took to get there. Okay, so if you have a very low pressure requirement for a given flux, that means it's very permeable, right? That should make a lot of sense, right? If you try to push water through some sand, it should go pretty well through it, right? Try to push it through clay, not so much, right? So the permeability of clay is very low compared to the permeability of sand. Goes to show why some places you can use septic tanks and some places you cannot. Okay, so that's just one more term. You'll have that equation as well. It's not adding a whole lot, just another way to describe kind of the porosity of a system. Porosity is its own term. We'll not go into that. Okay, so we have one more problem here, and what I'm going to do is I'm just going to recommend that you take a look at this for practice. Perhaps I'll even give it as a homework problem so that I can let you guys have a little time out today. But before we go, I will try to get you your next homework assignment posted today. If not today, then tomorrow. So you'll have that. You should have some time. You can ignore it over fall break if you'd like, or you can get to it during the break. So, okay. So with that, have a good fall break. Any last questions before we go? I'll also get your homework, your grades posted today or tomorrow, including exam scores. I do have exams if you didn't pick yours up yet. Okay. So with that, I'm done.